All right, hi guys. So today we're looking at standing waves and resonance in air columns. So if you remember last time we looked at interference and superposition. So we looked a little bit at the ideas of constructive and destructive interference. So basically when two waves overlap with each other, what happens to the resulting wave, right? And so we're going to expand on that a little bit more today. So when we're looking at resonance, we talked about this a little bit last time. Remember, we're looking at like the change in amplitude based on how two waves add together. So when two waves of identical wavelengths and amplitudes move through each other, then there's going to be an interference pattern that can be explained by something called the principle of superposition. And so basically what this is saying is that if the waves are in phase, then you have constructive interference happening. And all we mean by in phase would mean that if the crest and the crest line up, then we're going to have constructive interference. Whereas if we have waves that are out of phase, so then you would have a crest and a trough adding up, then destructive interference occurs. Okay, and we kind of looked a little bit at that last time. But essentially we can kind of look at this example that I have here. So we have wave A illustrated in green and wave B illustrated in blue. And then when those two combine to make a new wave, I've highlighted that in pink. So here we have two waves that are identical wavelength and amplitude that are coming towards each other, wave A and wave B. So here they are before they've kind of connected with each other. When we see them moving kind of in this first part, so essentially we're a quarter of a wavelength past on either side. So remember the wavelength is the basically the distance on the wave that it would take for the wave to start repeating itself. So if we think about looking at the combination of these two waves here, if we start at the bottom here, kind of by equilibrium, and then we go up, and then we go down, then it would be like right about here would be the new wavelength. And so right now, when we have these two waves coming towards each other, if we have about a quarter of that, so we're coming from the equilibrium and going up and then coming back down, so we're basically a quarter of a wavelength past on either side, then what we see here is that the trough of wave A and the crest of wave B are lined up with each other. And that's where we end up with destructive interference, because remember we talked about this last time, the amplitudes are going to add together. And so this higher amplitude, or the crest of wave B, is going to add with the equally low amplitude of wave A. And so then they're going to add up to zero, right? Because their amplitudes are equal. So if this was like +1 and this one was -1, then they add up to form 0. Then if we see now if they're in phase, so that here we can see the blue crest of wave B and the green crest of wave A are together, well, then we're going to have those two heights added together. So say if they were both 1 high, then the resultant wave is going to be 2 high, right? So double that height. And that's constructive interference. And then of course we're going to see the same thing happening with the trough. So if they're -1 amplitude, if both of them are -1, the resultant wave is going to have an amplitude of -2 because it's -1 and -1. Let's see. So moving on to think about a standing wave. So when the two waves pass through each other in the opposite directions, they're always shifting in and out of phase, right? Because they're moving along. So we're going to see a constant shift between this, where they sum up to nothing, and this, where we see them summing up to much larger than the original waves in terms of their amplitude. And so that's where we're going to see what's happening here at point D, which is where wave A is carrying on through here, wave B is carrying on through there, and together, when their crests and troughs are balanced out, it's going to be at 0. So that's when they're out of phase. And then when they're in phase, we're going to see this summative quality here. So the resultant wave is actually going to appear to oscillate or vibrate between fixed points instead of looking like it's moving through a medium. And this is known as the standing wave. So I'll show you guys an example of how that looks because it's kind of hard to visualize it without actually seeing it moving. But before we do that, let's just have a quick look here. So the resultant standing wave, so this is all highlighted in pink, so this is what you would actually be seeing, is that you're going to end up seeing that it's kind of like this trough is going to look like it's always switching places with this crest, and that's going to happen all the way down. So it's not going to look like they're moving left and right. It's going to look like the wave is just going up and down in place. You've seen this before if you ever have like a tight string that's tied between 2 points and you pull it and then you see it go kind of like up and down, vibrating. So that's what it looks like to us, right? It looks like it's just bouncing up and down, but in fact it's waves going back and forth and causing constructive and destructive interference. So with this resultant wave, in the points on that string, like if you were to have multiple, I mean, when we do a string, it's usually just one kind of crest and trough. But essentially, if you had multiple points, then the points where it looks like it's coming together or standing still at the equilibrium line, so I've highlighted those with the stars here, that's destructive interference is happening with the two waves that are passing through each other. And the points where it's high up or low down, so a crest or a trough, is going to be constructive interference. Okay, so that's when the two waves that are moving through each other are adding up to form that higher point. So if you want to see this, you can actually open up the notes for yourself. I'll just pull them over here. So I posted this in your notes, but basically you can double click on it and, oh, hold on a second here. Doesn't seem to want to happen in, maybe I can do this. There we go. So there you can see the wave moving through. So basically what's happening here is the red and green waves are the ones that are moving through each other in opposite directions. The blue wave is the resultant wave that we actually see. And so you can kind of see how it looks like the blue wave is just bouncing back and forth across the equilibrium line there, right? So that's the resultant standing wave. Okay, let's see if I can pull this back across. I might just have to line it up again a second here because I think it's not going to be. There we go. Okay, so hopefully that helps you to kind of understand what we're talking about here with the resultant wave or the standing wave. So we have some more terminology to look at in terms of these standing waves. So the first thing is we have nodes and antinodes. And so nodes are basically the points in the standing wave where there's minimum amplitude between the two waves. And so that would be, like an example would be here, we can see nodes are right here. And so it would be the same throughout, right? So we have minimum amplitude. So basically the two waves are summing together to add up to the equilibrium. Now, nodes always happen at closed or fixed ends. So if you do have like a string that's attached to something and vibrating, for example, then the end where it's attached would always be a node. So you're never basically going to see an end where the string is wide apart like that. So a fixed end is when, a string or a spring is attached to an anchor point, or the other time where we see these types of waves is in air columns. And so if we have a tube kind of like this, so if it was closed at one end or if it's open at both ends, with the closed one, we're going to see a node here at the closed end. Okay, and then antinodes are always happening at open ends. So the antinodes are always the high points here. And so at the open end of the tube, we're going to see that the wave kind of spreads apart or opens up. Okay, if we're thinking about a rope or a spring that's attached, the antinode is always going to happen at the end where it's free to move. And so that's going to be the maximum amplitude between the two waves. Now, an important thing to kind of be aware of is that the distance between neighboring nodes or antinodes is half of a wavelength of the individual waves. So if you look at this diagram here, here we have a node, and then if we go to the next node, that would be a half of the wavelength of each one of these waves, right? So if you think about what's going on here, we have the wave starts here, it goes up, back down towards equilibrium. So that's a half a wavelength, because the other half would be that it goes down back up to equilibrium, and then we would be restarting the wave, right? So we don't want to keep doing that. So this is the whole wavelength, and you can see that the distance between these nodes is a half of that. You can also like write it as the distance between the antinodes. So you could say from here, so then a half of a wavelength would go down, and then if I went back up, it would be the full wavelength. So from here to there would be a half of a wavelength. Okay. Let's see. Okay, so let's look at some examples of how we can actually start to draw this out. So in the example, it asks us to draw the standing waves that would be produced in an open-ended tube or in a tube that was closed at one end. So like we said, with the closed end, we're always going to see a node. So it's going to be basically in the middle, because the wave is going to oscillate with maximum amplitude of the width of the tube. So we always want to start with a node at equilibrium, which would be halfway between the two maximums. So right here. And then remember, we said the antinode always happens at the open end. So basically that means that at the open end here, we're going to see the maximum amplitude of the wave. And so it's going to go kind of like this. So it's going to kind of curve out, and that's going to be your maximum amplitude here. So this end would be the antinode, and this end here is going to be the node. Okay, now one important thing to be aware of here is, because you're going from the equilibrium to the maximum like crest essentially, or trough on the other side, then what is a good thing to be aware of is we're not even going back down to the equilibrium, which would be a half a wavelength like we talked about in the previous question. So actually what we have here is, sorry, this is not drawn in very well. There we go. Good enough. So it's, if you actually were to figure out this whole wave, you would find that the length of this tube is going to be, or the wavelength that fits into this tube would be another way to think of that, is going to be about a quarter of the wavelength is equal to the length of the tube. If we think that like from here down to here is our length, right, of our tube. So the wavelength is equal to, because we have a quarter of a wavelength in here, actually that shouldn't be, that's not correct. A quarter of the wavelength is located in this length. So actually if we wanted to say how long is the length, we would say that the length is equal to a quarter wavelength. Oh, I think that's what I had. I guess I talked myself out of that. Okay, and then, so then on the other side of that, we can say open-end tube column is going to have antinodes at the open ends, right? So what that means is, if it has an antinode here, it still has to like be forming the wave. So we can't just say that it's antinode all the way through. So instead, if it's going to start up, let's say up here, it's going to have to pass down through the equilibrium and then balance out at the other side there. Okay, and then same thing going up like that, right? So the wave, the two waves that are passing through each other, again, are going to have antinodes, but this time there's going to be an antinode at each end because it has to be open at the end, antinode. And then right here in the middle is the node. So think about, how does that affect the wavelength? Do you think we still have a quarter of a wavelength? Well, if a quarter of a wavelength is from the equilibrium to the top of a crest or a trough, or the bottom of a trough, or whatever you want to say, then no, right? Because we have one of those, and then we also have a dip down to a trough. So we actually have 2/4 or a half of a wavelength. So we can say, oops, I don't know why I put the wavelength there. We can say that we have 1/2 of a wavelength, which is the length of this tube. So the length of this tube is a half of one wavelength. Okay, let's see. So with all of this understanding, we can know that springs that are like attached to something and air columns or tubes have a natural resonant frequency at which they will easily vibrate when a standing wave is produced. As long as the nodes and the antinodes are in the correct locations. So essentially that means that whatever wavelength we're working with, right, whatever the natural frequency would be for what we're working with, we need to make sure that the length of the tube or the distance between fixed points, for example, for a spring, have to accommodate that specific frequency. Right, so we need to have an appropriate wavelength. So mechanical resonance can be achieved when a forced frequency matches the resonant frequency of an object. So if you remember, we talked about mechanical resonance, which is where the frequency kind of increases the amplitude of the frequency, right? So when a person blows over the top of an empty bottle or blows into an air instrument, the air starts to oscillate or vibrate and produces a standing wave. And so you're going to be able to hear the points of constructive interference. So basically the antinode locations where the maximum amplitude is going to produce the loudest sound. So you've probably noticed that if you're like doing the thing where you kind of like blow into a bottle or whatever to try and make sound, you'll notice that there's points where it makes like the loudest possible sound, right? And so these are points where you are producing a wave that essentially meets these requirements of having nodes and antinodes at the fixed points and at the openings. So the resonant frequency of the node or sound produced depends on the length of the air column. So here you can see if we have air columns of different lengths, and in this case they're using a tuning fork, but it's kind of the same idea as blowing into it. So you have a tuning fork that's producing a frequency, and so in this shortest one, that's able to produce 1/4 of a wavelength. If we increase it to the point where this next one here, so basically we double the length of the tube and we're still using the same frequency, it's doubled. Well, now we're going to have a node at the open end, which does not end up producing any sound, right? Because like we just said, we want to have the maximum amplitude to produce the loudest sound, and this is going to be the very minimum amplitude. So this one will not produce any sound, but then if we increase the length again, so now we have the 1/4 wavelength, the half wavelength. Now we're at 3/4 wavelength, which allows it to be open or have the nodes at the open end again. Now we're going to hear a loud sound again. And then again, if we increase it so that we have a full wavelength, again, we're going to see that that we have this, sorry, did I call that last one a node? Sorry, that should have been an antinode. And then if we lengthen it again, we have a node, so the minimum amplitude, and so again we're not going to see a sound. Okay. Yeah, so the fundamental frequency is defined as the lowest frequency that can be generated by the standing wave. And so that would be your longest possible wavelength, right? So fundamental frequency, if we look at these two examples, so either looking at an air column or a spring that's fixed at both ends, fundamental frequency would be this example or this example. And so you can see how those are the longest wavelengths because we have the same distance for all three of these examples, or in this case all four. But for this one, we only have 1/4 of a wavelength, whereas like for this one, we have, let's see, what would that be? 1 and 1 1/4. So this is a shorter wavelength, which is a higher frequency, and the fundamental frequency is always your lowest frequency, which is your longest wavelength. Same thing is true over here with the spring. We again have like a quarter of a wavelength here, and here we have, let's see, two wavelengths fit into the same length, right? So much higher frequency and shorter wavelength. Okay, so make sure that you're familiar with the fact that the fundamental frequency is the longest possible wavelength, because you'll see that come up in questions quite a bit. So it's good if you can kind of recognize that. So let's call it fundamental frequency. Okay, and then the same thing would be true over here. So those are both the fundamental frequencies. Okay, let's try doing some problems with this, because that's mostly what we'll be doing with these types of questions, is doing calculations with them. So we have a closed air column that resonates with a fundamental frequency of 225 hertz. Okay, so I've written down the variables already. What is the length of this air column if the speed of sound is 341 meters per second? Okay, so we have frequency and we have velocity, and we want to figure out the length of the column. So I'm just going to do a quick little sketch here of our column. I don't know, that's about the same size. There we go. Okay, so if this is our column, now it's asking us specifically that we have a resonation or a resonance at a fundamental frequency. So we want to be able to draw the fundamental frequency of a closed air column. Okay, and so when they say closed air column, they always mean closed at one end. And so the first step that we need to do with questions like this is think about what would the fundamental frequency look like. Well, in a closed air column, like we just mentioned, it's going to start at a now I'm worried I'm going to have my names mixed up here. So we're going to start at a node, and then we're going to move to an antinode. So we're going to go kind of like that, right? So the fundamental frequency is always going to start with your node and move to your antinode, and that's always going to be a quarter of a wavelength. Okay, and so essentially what that means is if we can figure out the wavelength, then we know that a quarter of that value will be the length of our tube. Okay, and so that will help us to solve for length. So do we have a formula that relates frequency, velocity, and wavelength? Well, yes, we do, right? In our waves here, we have velocity is equal to frequency times by wavelength. So velocity equals frequency times by wavelength, and we just want to rearrange that to solve for wavelength. So we'll have to divide out the frequency. So it'll be wavelength is equal to velocity over frequency. Okay. Let's see, and then, so we'll be able to solve for the wavelength, and then once we have our wavelength, we can figure out the length of our tube, which is what we just said, which is that a quarter of our wavelength will be equal to 1/4 wavelength is equal to the length of our tube. So if we want to solve for length, we're just going to have to do this component here. So this will be our second problem solving step, and this one will be our first problem solving step. Okay, so step number 1 is just going to be wavelength is equal to our velocity of 341 meters per second divided by our frequency of 225 hertz. Okay, and that gives us 1.515 repeating meters as our wavelength. So number 2 would be a quarter times by our wavelength of 1.515 repeating meters is going to be equal to our length. And that gives us 0.378 repeating meters. So we can say the length of the tube is equal to, if we round for sigdigs, we need 3 sigdigs. So if the 8 is repeating, there's an 8 after that, so we need to round it up to 0.379 meters. Okay, so that's kind of an introduction to those types of questions. I think we'll look at some stuff that's a little bit trickier. So the next one is we have a 0.60 meter string vibrating at a fundamental frequency of 125 hertz. Now the tricky thing with this is that anytime you have a string vibrating, what does it mean has to be happening? Well, it means that it has to be closed at both ends. Right, because if it's free at one end, it just kind of flops around. So closed at both ends. So that's going to help us because, again, we're working with a fundamental frequency. So we basically need to be able to think about, I guess I don't really need a ruler for this one. If it's closed at both ends, what is the wave going to look like? Well, for a fundamental frequency, remember it's only going to be a quarter of a wavelength. So we're going to see that it'll go down and up. Okay, so that would be like the fundamental frequency. And it says that it's 0.6 meters. So let's say from here to here, we have a length of 0.60 meters. Okay. So then we also know that 0.6 meters is about a quarter of the wavelength, right? Oh, wait a minute. Sorry, I'm not thinking properly. That's a half because we go, this one would be a quarter and that one is a half. So let's just think about that here. We have 1/2 of a wavelength is equal to L. Okay. So, in this case, we're looking for the speed of the wave through the string. We have the frequency. And we have the length. So thinking back to what we just did, if we want to solve for velocity, we can use our formula here. So velocity is going to be equal to frequency times by wavelength. But we need to solve for our wavelength first. So our wavelength is going to be equal to, let's see, if our wavelength is, if a half of our wavelength is in the length, then we would have to double it for the full wavelength, right? So we could say that wavelength is going to be equal to, and it's the same as doing it algebraically, right? Because I have basically a half times by wavelength is equal to L. So then if I do L, let's see, if this is being multiplied, I would have to divide it out. So length divided by the half is the same as length times by 2. So I can say wavelength is equal to 2 times by the length. Okay, so that would be my first problem solving step, and this one will be my second problem solving step. So number 1, wavelength is equal to 0.60 meters is a half a wavelength. So I want to multiply it by 2 for the full wavelength, and that's going to give me 1.20 meters. Okay, and then for step number 2, we already have the formula arranged the way we need it, so it's just going to be velocity is equal to our frequency of 125 hertz times by our wavelength that we just found, 1.20 meters. And that gives us 150 meters per second. Now we are limited to 2 sigdigs, so in our final answer we're going to have to say V is equal to 1.5 times by 10 to the power of 2 meters per second. And that's our final answer. Let's see. Next question. If you made an open-ended column longer, explain what would happen to the fundamental frequency. Okay, so we have an open-ended column, so basically that means that we have to have the antinode at both ends. So that means we would basically have to go, ooh, I wish I wouldn't have made these quite so big. Kind of like that, right? Okay, so if this is our shorter tube, right? So a half of our wavelength is the length. Now with a longer tube, they still have to have antinodes at either end. So even though you're lengthening the tube, you still have to see the same shape of the wave in there. So first of all, we can think about what is going to happen to the wavelength. Well, if half of the wavelength is now longer, like say if this was 1 meter and this is 2 meters, now half of our wavelength is 2 meters instead of 1 meter. So our wavelength becomes longer, right? And so what does that tell us about the frequency? Well, as wavelength increases, we know that frequency decreases, right? The amount of times that the wave passes by is going to decrease because the wave is longer. So we can say as length increases, as length increases, wavelength increases. And that means that frequency, so we can say therefore, which is represented with that little triangle of dots, therefore frequency decreases. Okay, so the important thing here is to be aware that that if you lengthen out your tube, the shape of the wave inside of there is still going to be the same. Okay, it's just going to be the wavelength and the frequency that will change. Let's see. Last question here. We have a tuning fork with a frequency of 256 hertz is held above a tube filled with water. The water level in the tube can be adjusted, which will change the length of the air column in the tube, right? So you can add water in or you can pour water out. What is the distance between two adjacent points when the mechanical resonance is the greatest? So we want to think about what do we know about what makes mechanical resonance the greatest? And then they also give us the speed of sound here. Okay, so essentially they're asking us for the distance between any two adjacent points, so it doesn't really matter if you choose antinodes or nodes. We just want to know what the distance between those would be. And so you need to think about what is that distance? What's the distance between two nodes or two antinodes? Well, if you look at kind of what's going on here, again, we can think, okay, if we start at the bottom and then we go up to the top, right? So that would be the antinode here. So looking at just one wave, we've done a half of a wavelength, right? Because we've gone from the bottom to the top, and then to complete it, we'd have to go from the top to the bottom. So we're at a half of a wavelength, so we can say D is equal to a half of the wavelength, which is the same as saying wavelength divided by 2. Okay, and so that's how we're going to figure out what this distance is in the end, but we need to know wavelength for that. So how can we solve for wavelength? Well, if we have frequency and velocity, we can use the formula we've been using all along, as long as we just rearrange it so that wavelength is equal to V over F. Okay, so that's going to be our set of problem solving steps. So we're going to say step number 1, our wavelength is equal to the velocity, which was 343 meters per second, divided by frequency of 256 hertz. And that's going to give me 1.3398, something like that, meters as my wavelength. Okay, and then remember, I'm working with a half of a wavelength for the distance between nodes or antinodes, just adjacent points. And so my distance is going to be equal to the wavelength that I calculated divided by 2. Wavelength over 2. You can also do a half multiplied by, so I've kind of shown you guys both in this problem solving set. Doesn't really matter, whatever you're more comfortable with. I usually actually do find that setting it up this way can make algebra a little bit easier if you're doing rearrangements. but it's not necessary. Okay, so wavelength divided by 2, so 1.3398, something like that, meters over 2 gives us 0.66992 meters. And so as our answer, we can say that we have 0. Rounding for sig digs, what's the least we had there was 3. Is it 3? Yeah. So it'd be 0.669, which is actually going to have to round up to, that 9 is going to round up that 6, so it's actually 0.67, whoops, not 0.06, 0.670 meters. Or if you wanted to, you could always say 67 centimeters. And it's a good idea to be able to do that conversion between those two, especially if you're working with multiple choice, because this could be the way that the answer is given, so you'd want to make sure that you could do that conversion. Okay, so you guys have some practice problems you can try out of the textbook to kind of expand on that. Some of the questions do get a little bit more challenging, but basically I find that the main challenge that they introduce with these questions is doing multiple calculations to build on each other. So the actual ideas shouldn't get any more complex, but sometimes they make you do a lot of calculations to solve one of the problems, but they are definitely good practice. Okay. Oh, and actually this will be an example of one of those ones. So this is kind of like a standard of excellence type of question. So basically you're looking at experimental data. So if you were doing this lab in class, this is actually what you would do, and then you would do the calculation. So she's figuring out basically different distances that you can fill a tube with water, just like we just looked at, and then figuring out where you can hear something. So that means that there's a fundamental frequency happening there, or a multiple of that, right? So in this case, you're looking at an open-ended tube that's being filled with water. And so because it's open-ended at one end, essentially the places where you're going to hear the sound are always going to have the antinodes at the opening. So you need to kind of keep that in mind while you do your calculations. And then you want to figure it out for these different distances. Now the tricky part that sometimes comes up with these is make sure you're careful to think about what the actual distances are, because they give you the distance, like the length of the tube, and then they tell you how much water is being filled in. So think about, are these distances the distance here, or are they the distance here? Because the distance you need is the air component, not the water component. So just be careful with your distances for that question. Okay, and that's everything for now. And next time we'll be looking at our last set of notes for this unit, which is the Doppler effect.